ask it would be recorded. So this is a study seminar on differential equations. And I need to warn you now, I never studied a course on differential equations. So everything I know about differential equations has been gleaned from helping students in the Maths Learning Centre. And also I asked one of the students, thank you very much, can't see, thank you very much, to send me the past exams, and a different student sent me the notes so that I could try and figure out what the hell is going on. So what I did is I went through the notes and I wrote down every piece of terminology that was in it for myself, which I think is a good plan for you, and this will not make any sense to you because I have doctor writing. That's why I'm so good at helping the med students. So I wrote down everything that your notes said about what every word meant. And that was sort of half helpful because at least I knew what some of the words meant, like reduction of order, for example. And then what I did is I sort of went through the different types of differential equations you've seen and drew a picture of how they're related to each other. I thought I'd start by drawing the picture that I got. So there's ODEs, ordinary differential equations, which apparently means that it's just an ordinary derivative, it's not a partial derivative. So it's like a straight d, d1, dx, something like that. And the ones that you've seen how to cope with, they come in different orders. So there's first order, and there's second order, and there's higher orders. I'll write a neat version of this and put it online sometime between now and Monday. Okay, so the first order ones, most of them you saw at some point in the past in the dim dark ages of Maths 1B, and there were linear ones, which meant that you could rewrite them like this. Something like that. I know it's usually R, isn't it? And there were separable ones, which means that you could rewrite them like this. And then the new one that you learned this year was the exact ones, which meant that it was looking, you could rearrange it to look something like this. Okay? And there were methods, the linear ones you could use an integrating factor. And the separable ones you could separate it. And the exact ones, you had to use partial derivatives. So you had to say u equals crap. You had to say that the partial derivative of u, this is right, isn't it? du on dx was equal to m and du on dy was equal to n? Or was it the other way around? You see, this is the problem. Yep, I was right. Du on dx equals m and du on dy equals n. And n went with the dy. Yep. And then what you'd do is you'd partially integrate the m and then partially differentiate it with the other variable and everything would work out. But I'll do an example of that if that's what you want me to do at some point later. At the moment I'm just writing down what goes with what. Okay? So that was first order. And that's pretty much everything I could find in your notes about first order differential equations. And then there was second order, and I'm going to move this over. So that's why I said I'd write a neat one afterwards, because I'm partly making this up as I go along. So then there was second order, and most of differential equations was about second order differential equations. You kept seeing Bessel and what's his name? Yeah, they all had names. And so you kept seeing all these ones that had names, and they were differential equations of second order. So your second order ones came in these flavours. The only ones you actually were taught how to solve were linear ones. Though presumably there are other types, but they're the only ones you were taught how to solve. And there were ones with constant coefficients, and there were ones with variable coefficients. So your constant coefficient ones were the ones that you did way back in Maths 1B. And they came in flavours of homogeneous and non-homogeneous. And your homogeneous ones, you had to use the characteristic equation to solve them. Your characteristic equation helped you to solve them. Or you learned a new method for solving them, which was to convert them to a system of linear in differential equations. Or convert to a system. Okay, so you learned a new method of solving the constant coefficient ones by converting them to a system. And the non-homogeneous ones, you had to do your particular solution and your homogeneous solution. So you did your y homogeneous plus your y particular. And so your y homogeneous you got that way, and your particular one, you either used undetermined coefficients or you use this variation of parameters. So your variation of parameters was a way of finding your particular solution. That's really not very clear. And that was the constant coefficient differential equations. Okay, lovely. And we'll go into detail on all of them. I just wanted to organise it. So then, off the side somewhere, on the next page, there's the ones with variable coefficients. And those ones, instead of having just constants next to the y double dashed and the y dashed, what you ended up with was functions next to those. And the majority of the ones that you saw had polynomials there. It was like x squared y double dashed and 3x plus 1y and those sorts of things. Okay? And since we are able to solve these from 1b, the biggest part of DEs in Eng Maths 2 was about your variable coefficient second order differential equations. So my understanding is that you have homogeneous and you also have non-homogeneous. And the relationship between your homogeneous and your non-homogeneous was the same. You first need to find your homogeneous ones and then you need to find the non-homogeneous ones. But the methods of dealing with the non-homogeneous was to do, you still got your y homogeneous plus your y particular, but to do this we had to do variation of parameters. And that was the only way we had to do it for variable coefficient ones. And then the homogeneous ones, you saw a few methods that if you knew one solution you could figure out the other one. And there's only been really one real method of finding a solution from scratch, which was to do a power series, really. That's the only one I could find in there, which is also known as the Frobenius method. That was the only one I could find. It was actually a way of finding a solution to begin with. There were plenty of questions in tutes and things where you were given a solution and you had to find another one, but or you had to check if it was really a solution, but the only one I could find that actually had a way of finding it from scratch was with the power series. And then if you want your second solution, if you didn't get one from the Frobenius method, you could use reduction of order. And reduction of order is so important to your lecturer that he's put it on the formula sheet, so you must think it's important. Okay, and that was everything that was really there about solving first and second order things. Now, that took up, most of the course, but that's my way of organising it. I wanted a way of saying, well, what the hell, how do I figure out what goes with what? And that was my way of organising it. But there is one more. You did do some higher order ones. Because in one of the assignments there was like a third or a fourth order one, and the only way you had to do that was when you had linear and constant coefficients, and what you did then is you converted it to a system of differential equations and used matrices, which I'll talk about in just a moment. So that was ODEs. That was simple single ODEs, and that was how we dealt everything you've been shown about how to deal with them. And then there was also the thing of systems, and as far as I can tell, the purpose of doing systems was to do fluid mixing in tanks. I'm sure there are other reasons, but that was the main example that was in the lectures. And it's also to help solve these higher order linear constant coefficient differential equations. Actually, you could do it. Instead of converting to a system, you could just use your characteristic equation as well. That's another option. And they both came out to the same thing in the end. But in at least one of the past exams, the lecturer thought it was so important to know how to convert to a system that they asked you to do it. So it's good to know how to do that, apparently. Right. So that was ODEs. Then there were systems. Of ODEs. Now, you'll notice I'm not writing down the definitions of these things because they're all in the notes somewhere. And what was really important to me was that if I was doing an exam like this, doesn't seem to be common for him to ask, is this a linear equation? Doesn't seem to ask that sort of thing. What he does seem to ask is, solve this equation. So knowing which is sort of less important. You still need to know, but he'll often tell you, solve this second order linear equation. So he tells you what type it is anyway. So I thought it was more important to know what to do with them. So when you had the systems of ODEs, apparently there's actually any number of those types, and they can be linear and non-linear and homogeneous and constant and non-constant coefficients. And there's all different types, but the only ones that are actually in your course, because he put it in big red writing, was the ones where it was linear with constant coefficients. Okay? So only linear with constant coefficients. That's what he said in his notes, so I'm presuming it's true. And what that means is that you'll get all these different functions, and you'll be able to write it as something in terms of the others. And these things here would just be linear combinations of y1, y2, y3, and so on. So this would be something like a1, y1 plus a2, y2 plus a3, y3, and that sort of thing, okay, where those are just numbers. And what you can do is you can convert this into a matrix or vector form, as he called it, and you can say that is A1, A2, A. Like that. And then there'll be other stuff here, right? So apparently you can convert this into a matrix. And what he calls this is, he calls this sort of bold y dashed is matrix times bold y, where in text I have to put an underline. And that's what they were, and then the methods of solving them was to find the eigenvalues and eigenvectors of the matrix. So, use So what I'm doing here, without giving you any details or examples, doing exactly what I would do to study a maths course and sort of run through the whole thing and just write down what everything is and the names of the methods for solving stuff, so that at least I have it organised before I start looking at the details. That's how I study statistics as well. There's all these statistical procedures, the t-test and you didn't do very many of them, but paired t-tests and unpaired t-tests, and I just write them all down and what situations they go in, and then I start dealing with what they actually are and how to do them. Okay, and that was pretty much everything for systems of ODEs. There were some details about what to do with the complex eigenvalues, and I'll deal with that when you ask me in a second. And then, I'm going to skip Fourier series for a second, and then there was PDEs, which was partial differential equations. Oops, I should be writing in pencil because that's my system, isn't it? That's too late now. And you were showing like all these different formulas that had names, like the heat equation and whatever, and they were all partial differential equations. And it was like a U or something, and it had an x and a y to differentiate it with respect to, and there was some partial derivative equals some other partial derivative. And what you've been taught is there's a few examples where you had some substitution and you subbed it in and it turned into something else. But what you've been taught is this thing called separation of variables. And that's what that is for. And it involves eigenvalues and infinite series and all those sorts of things, but that's what that process is. And then finally, there was this whole thing on Fourier series, which is apparently useful, but you don't seem to at any point actually use them to do differential equations. So correct me if I'm wrong, but I couldn't find an example where he actually used it to solve a differential equation. There was one example where he said, oh, and look, the answer is a Fourier series for something or other, but that was the extent of it. Is that your experience too? I couldn't find one. But it seems to be this whole discrete part of the course that you still need to know about. And I think it's something to do with the fact that if you're going to do Eng Maths 2B, that you're going to start at Fourier series and move on from there, I think, when you do some of the differential equations there. So, I think. I'm having a chat to Barry now, who's the lecturer for that, about what sorts of things I should put on my website to help you, because I won't be able to help with Eng Maths 2B. But I can at least say, here are some things that, if you're feeling motivated, you could look up to remind yourself of, because he's going to expect you to know, such as integration by partial fractions. Okay, so Fourier series. What you did is you got your function, and what Fourier series was a way of rewriting your function as an infinite series. Of sines and causes. I put apostrophes there because sine and cos are both abbreviations, and that's the appropriate thing to do according to the signs on the writing centre's wall. So, that's what Fourier series were for, and what you had is different kinds of functions, and you managed to turn them into Fourier series in various different ways. So there was ones that were already periodic, periodic functions, and there were ones that had period 2 pi, and they used apparently the Euler formula. Crap. With all those little integrals. And then there were ones with period 2L, which had slightly different formulas. And then there were ones that weren't already periodic, and you had to create a periodic extension. So there were ones that sort of went from 0 to somewhere. And then you had to do like either an odd extension or an even extension, or sometimes just an extension, because there was that assignment question where it was sort of something flat and then like that, and it wasn't either even or odd. Just some other extension. And then they were periodic, and so you were able to go back to the method over there and use those methods to find them. And that was Fourier series. That was my organisation of it. And it's interesting because when you guys came to ask me about Fourier series in the drop-in centre, I was like, oh my God, what's going on here? But when I sat down to look at it, it's actually quite a small topic. There's not actually all that much in it. So that is my organisation of your course. I probably missed the Ronxian there somewhere, which was way back when deciding if your solutions to your homogeneous one were independent or not. And that was pretty much my assessment of what's in your course. There you go. So the rest of this is you request David to talk about something. And I'll probably talk about everything, but much like a Christmas carols request session, we'll sing all the famous ones, but we'll just sing it in whatever order you decide. So it's the same deal, but with Fourier series and differential equations. So, and you are allowed to ask about past exam questions, even though, Trent has tended to tell people to go away if they do that. You are allowed to ask because I will still talk about it. So, anyone brave enough to put in a request to talk about any of those things or something else?
Can I request a topic, or do you have questions there?
I've got, yep.
Linear variable, non-homogeneous variable coefficient, ODE.
Okay.
If you have one.
So non-homogeneous, linear, variable.
It's where you have to use variation of parameters.
Okay. So non-homogeneous linear variable coefficients, and we're apparently supposed to use variation of parameters. So that would be like a second order, right?
Yes.
I love how you can, it's like doing German. You can just tack everything together and have a great big description of a differential equation. There's like 4 pieces of information there, 5. Okay, so we're looking at, do you have a particular exam question or question in mind?
No, sorry.
That's all right. Okay, well I'm just going to go to the lecture notes and see where that is, because I have a feeling it's actually quite near the beginning. Here it is. It's in lecture 4. Okay. Cool.
There's an example of the 2012 exam.
Is there?
Question 2.
Yay. It's going to do one of the ones in lectures, but you guys can tell me what I'm doing right or wrong. So 2012, question 2, consider the non-homogeneous ordinary differential equation such. Okay. So 2012 question 2 from the exam. So we've got x, y double dashed, minus 2, x minus 1, y dashed, plus x minus 2, y equals 1. Okay, and it's non-homogeneous because it's not equal to 0, and it is linear because these are all just functions of x times y and its derivatives. And my screen is... See if I can get it to focus properly. No, it's just crap. And it's and second order. Cool, we're all good. So, it says in the exam to use a substitution to show that the associated homogeneous equation transforms into a linear blah, blah, blah. Okay, so apparently if it's non-homogeneous, we should always convert it to homogeneous first, and that's what I said. So, homogeneous version. Okay, and you need some method for finding one solution so that first you can get, so that you can use your variation of parameters to find another, variation of parameters finds a particular solution. Okay. And so I'm going to skip that bit, so unless you don't want me to. Yep, cool. And so you use a substitution. So if you're supposed to use a substitution, he always tells you which one, because he hasn't taught you how to choose which substitution to use. Every time he's told you to use a substitution, he's told you what it is. Okay? And we're supposed to sub that into this one and transform it into one with constant coefficients. Yay. So presumably, we need to find the derivatives of y and sub them in. And then everything will be terms of u and x, and I'll be able to have one that's got u's and x's. Okay? So, dy and dx. Do not like it, Sam, I am. I'm going to use the product rule because I don't like the quotient rule. No. Someone tell me about how the substitution thing goes, because I can figure it out now and then I'll tell you. How does it go? Like, because you always get crap in the middle. So what happens in the middle when you do these examples? Has someone got one of the examples from the lecture notes that I can pull out and go, what the hell did Trent do? Because I need to do it. Because you see, the thing is that this revision seminar is not David knows everything and tells you. This revision seminar is David knows the same stuff as you. Less, because I wasn't at the lectures. Yes?
So we just differentiate it once, twice, and then sub them back in for y, and then we're given another equation that it's also equal to.
And it should...
Do like, you relate the coefficients to the...
Alright. So you're telling me I should do, so like, du on dx like that?
Yeah, you do the derivative and then the second derivative, and sub it back in.
Okay. Alright. So I've done the first derivative. And then I sub it back in. No, first I do the second derivative. And so I'm going to have to use the product rule again. So derivative of that would be d squared u on dx squared. Keep dx to the minus 1. Keep the du on dx. Differentiate that. And this one will be du on dx, x minus 2. Okay? And apparently, if I just sub everything in, it should all just cancel out. That's the idea?
Are we given another equation that it's equal to?
No. But we've got the differential equation we can sub it into. So, you've got one?
I think so. Right, yeah.
Yeah, that's pretty much what our friend over there said to do.
You divide through straight away by that. So you've got just y double prime that
Uh-huh.
front, and then sub it in.
Yeah, it doesn't have a substitution in it. Oh well, it's worth a try. Okay, so I'm just going to, you can see the pain that happens when you try and figure these things out without already knowing what to do. But Nicholas keeps saying to me, and it's probably a fairly rude thing to say, but Nicholas keeps saying to me that Engineering Maths IIA isn't that hard. I'm not sure I believe him, but I think his point is that there's only a small number of actual bits of information in Engineering Maths 2, and you keep being asked to do the same stuff, so presumably it should work if you just give it a go. So I should be able to go therefore that x y double dash minus 2 x minus 1 y dashed plus x minus 2 y equals 0. And I can sub that in. So my y double dashed was, let's see, u double dashed times 1 over x minus u dashed times 1 over x squared minus u dashed times 1 over x squared plus 2u over x cubed. And my y dashed was, back up on the previous page, u dashed times 1 over x minus u times 1 over x squared. And y was u over x. So apparently I should be able to just expand that all out and see what I get. So let's see. I've got u double dashed. There's two of those, aren't there? Minus 2u dashed times 1 over x plus 2u on x squared. Okay. And then I've got minus 2x minus 1 times u dashed on x plus 2x minus 1 times u on x squared minus u plus 2u on x. They don't give you A3 paper to write on in the exam. Perhaps some of this seminar is David feels your pain, so you don't feel so bad because someone else feels the same way. Who's presumably clever enough to get a PhD in maths, and so if he finds it hard, you can't feel so bad. So this one here, 2u dashed plus 2u dashed on x plus 2u on x squared. You're going to tell me something? Have I done something wrong?
Yeah, there's supposed to be a plus instead of a minus earlier on.
Where?
So where you're the second to the last line on that top page. So, and then yeah, right there. Yeah.
There?
Yeah. Because it's plus 2 x minus 2 y.
Totally is. Which turns this into a... which turns this into a plus and this into a minus. So, let's see. 2u dashed on x, and there's a plus 2u dashed on x, so they cancel each other out. There's a 2u on x squared.
Were we supposed to put this in standard form before we started?
No, because it actually makes it easier usually. if you leave the x at the top, because it helps things cancel out at the bottom. Everything's supposed to cancel out, right? Have I got some minuses wrong then? Oh, bloody hell. It's all supposed to be so nice to say, hey, look, everything works so prettily and it all cancels out. That cancels with that. Yep. This isn't supposed to be an x squared, is it?
Here it is, look at the line above it.
It says 2u on x. Or maybe that's supposed to be an x squared.
No, the one on the right should be an x squared because the last line
Look
got
directly above
plus 2 minus 1 over then u on x squared.
Ah! This one's supposed to be an x here. What about this bit? Oh. This is why you come to the Maths Learning Centre, for me to find these errors for you. It's all supposed to cancel out, people. I'm presuming that this is supposed to cancel out with that, because then it will be first order linear.
It does in the answer somehow.
It does in the answers somehow.
Should we just skip to the answer?
What does? Yeah, David gives up, right? That's the great story.
Turn out that u double dash x.
Somehow, and in the exam you'd go, I've done something wrong, they're supposed to cancel out. Well, you know, if you can't solve it, you might as well do something. Okay? But look, there's no point giving up on your exam just because it doesn't work out the way it's supposed to. You've got to write something so you can finish it from there. They'll give you marks if you continue from that point. So somehow they're supposed to cancel out, unless I've missed something else. Maybe this is supposed to be a minus and that's supposed to be a 2 on x, but it doesn't look like it. Oh, this is a 2u on x here. Ah, there we go. This cancels with this, and this cancels with this. Yay! So moral of that tale is probably best to be a little longer with your expanding and don't lose all your minuses and your x's. That is first order constant coefficients. But you're right, at some point you should have said, if you can't find it, you could go, well, these are the bits that involve just the u's and the u dashes. Everything else is supposed to cancel out. So what do we get? Now it's second order constant coefficient linear, and we can go all the way back to dim dark ages of Maths 1B and solve it. So first we do our characteristic equation. And then I factorise it. Is that what the solutions say?
The u double dash take u dash plus u was right. Yeah.
So we get one solution. If we'd gotten two, it would have been e to the something and e to the something. So we've got our linearly independent solutions are e to the x and x e to the x, because it's e to the lambda x, and because it's there twice we have to put an x in front of it. Okay, but that's u, right? But u is in fact, but y is in fact u over x. So y1 is e to the x over x, and y2 equals x e to the x over x, which is e to the x. He's called them the other way around, so I'll just switch that. I'll switch it back here. So in the exam, he said that y1 and y2 were the other way around, so that's what I'm going to do as well. So what happened here? Yeah, all sorts of crap happened in the middle, but we'll skip that. Oh, I turned it off. What did we do here? So with our substitution, we figured out the derivative, and we figured out the second derivative, and that was using the product rule. And then we subbed it all in, into the differential equation, and then did some magic in the middle, and it came out to this. And that turned it into something we knew how to do in a different way, and so then we did our characteristic equation, and then we subbed them back into what y was, because right at the beginning y was equal to u over x back here. So we subbed them back in, and we got these solutions here. Okay? So that would mean that the homogeneous equation has, not that he asked you to do it, but it's just worth pointing out. So my general solution to the homogeneous equation is YH equals like A plus B e to the x. Because I take the two solutions I got and I do the constants times each of them and add them together. Because that's what the theorem says about linear second order equations. And now we're up to the bit that someone actually wanted me to do, which was use variation of parameters to find a particular solution of the original equation. Now, variation of parameters uses a formula. Here we go. Variation of parameters is a method for finding a particular solution of your second order non-homogeneous linear ODE with constant coefficients using the solutions of the homogeneous case. So first you have to rewrite your original equation as standard form. Okay? So let's see. My original equation was x, y double dash minus 2, x minus 1 y dash plus x minus 2 y equals 1. And standard form has the y double dashed all by itself. Okay? And I also have to have solutions to the homogeneous case. So solutions to the homogeneous case are y1 equals e to the x and y2 equals e to the x over x. Yep. And then you'll see I'm referring to a list that I made. What I did is I went to an example and I wrote down everything that happened in the example. And so every time I do it, I'm just going to give those things a heading. So even if Trent doesn't give them headings, it's a good idea to give them headings yourself, because then you can see what's going on. And the person marking it can see what's going on, so it's easier for them to find things. So then we're going to write that yp is equal to u times y1 plus v times y2. Okay? And technically we're going to assume that u dash y1 plus v dash y2 is 0, but you don't need to worry about that, I think. But I'll just put it there anyway. Assume u dash y1 plus v dash y2 equals 0. Because that'll turn it into a system of differential equations which you can solve using the Wronxian. Now, did he give you, is variation of parameters on the formula sheet? Someone got one? Should be on last year's exam, but I printed them out very small. So. Oh yeah, here we go. Yes, variation of parameters is on the formula sheet. Cool, so we don't have to remember this ourselves. So then it says that what we get is we solve to get this, and you don't have to solve it yourself because the solution, the formula sheet says that we can. It says we'll get u dashed equals minus y2 times r on w, and v dashed equals y1r on w, where r is this, my rx, over here, there, that's my r, and w is the Wronxian of my two original solutions. So I'm going to need to figure out the Wronxian. So let's see. So I've got y1 was e to the x, and I need y1 dashed, which is e to the x as well. y2 is e to the x on x. y2 dashed is, let's see, differentiate the top, keep the bottom, minus, keep the top, differentiate the bottom, all over bottom squared. And the Wronxian would be the determinant of that matrix. So W is the determinant of e to the x on x, e to the x. Let's just write that a bit simpler. E to the x over x take 1 on x squared. That's a bit better. And I have to figure out that determinant, and that would be the Wronxian. So, okay then. E to the x times e to the x minus 1 over x squared, minus e to the x times e to the x over x, which is awful. But we will not be daunted. E to the x times e to the x is e to the 2x. X take 1 over x squared minus 1 over x. Oh, awesome. Look, x over x squared is 1 over x. So x over x squared is 1 over x minus 1 over x squared minus 1 over x, and that cancels with that. So we get minus e to the 2x over x squared as my Wronxian, or however else you're supposed to pronounce the thing. Okay, so that means that I can figure out what u dashed and v dashed are. So let's see. U dashed was minus y2 r over w. So y2 was e to the x over x, so minus e to the x over x. R was 1 over x. Yep. And w was minus e to the 2x over x squared. So my minuses will cancel. Be able to times top and bottom by x squared. E to the x over e to the 2x, which is e to the minus x, because you subtract the powers. Woohoo! And v dashed is y1r over w, and y1 was just e to the x. So I should be able to multiply top and bottom by x squared minus x e to the minus x. Really? Now I have to integrate them though. So, how many marks is this worth? Well, for the whole thing. And this is part C. Right, of course. It's a 2-hour exam. So, I don't really want to make you feel bad. Anyway, so u is minus e to the minus x, because that's the integral of that. We don't need the plus c, because we're going to multiply it by my y1. And v is the integral of that, for which I would have to use integration by parts. What? Someone's saying switch something around. No? We're not going to be so... Okay. So we shall differentiate that one. So minus x minus e to the minus x. U dashed is minus 1. V was minus e to the minus x. So x e to the minus x minus minus minus, which is x e to the minus x minus e to the minus x, which is x e to the minus x plus e to the minus x. Woohoo! And now, we're not quite done, because this just tells me what the u and v is, and right back at the beginning I said that yp was u times y1 plus v times y2. So, yp is u times y1 plus v times y2, and u is minus e to the minus x, and y1 was e to the x, and v is x e to the minus x plus e to the minus x, and y2 was e to the x over x. And so I can expand that out. E to the minus x times e to the x is e to the 0, which is 1. So this times that would be 1, because the x will cancel with the x on the bottom, the e to the minus x will cancel with the e to the x, plus 1 over x. How unsatisfying. But that is variation of parameters. So, is that the answer that Orm's got? Yes. I have the same answer as some other student. So, here we go. Let's just see what happened there. First I had to rewrite in the standard form, and the only reason to do that was so that I could figure out what the Rx was in the standard form. Then I had to go back to my homogeneous case and get those solutions. And somewhere on my page I need to write uy1 plus vy2. And then my formula sheet told me that this is what the answers for u dash and v dash comes to. I need to find the Wronxian. So really, this was all finding the Wronxian. And then I had to find what u dash and v dash were. And then I had to integrate them. And then I had to put them back into yp. So if I was being really good, I should probably have back here said find the Wronxian, and here said find u dashed and v dashed, and here said find u and v, and then finally at the end said find the particular solution. Just so that I don't have to draw boxes around it, because that would be actually annoy the marker, but just so that the marker can see what I'm doing at any given point. And I can too when I go back and check my work, if I have time. Okay. Yay. I do want to tell you something extremely important about drawing odd and even periodic extensions, because people have been asking about that. And one of the exams has a wrong solution for that from the Orm's questions. But before I move on, was there any questions about that variation of parameters thing? Yep.
So does that only work for non-homogeneous linear variable coefficients?
It should work for homogeneous too, but you don't need it because the particular solution is 0. And you haven't been shown any other type of differential equations.
And so what was the actual variation of parameters part? Was that part C?
Yes, part C was the variation of parameters. So the first bit was really a substitution, which is not really a formal method that you've been shown, you just have to know how to do it. And the second part was constant coefficients, and the third bit was variation of parameters. Odd and even extensions. Feel free to leave if you want to. I haven't booked Flenchy because I assume that no one wants to use it. On the booking system, it says that it's booked out all day for teaching. So everything I've got after here will record. I've asked it to record for 2 hours. If you do need to leave, I'll give you a couple of seconds to do that. But I will power on. We've got the formula sheet. Y1R over W. Oh, what did it come out to? That. So because it was two things multiplied together, I had to use integration by parts to integrate it. Sadly. Yep.
What was it? R was in R.
Yeah, the R in this is the Rx from your. It's the Rx from your standard form.
And one of them's negative, the other one's positive.
Yeah.
Is that straight out of the road?
It's actually on the formula sheet that's in the exam. Technically, the minuses and pluses come from the inverse of a 2 by 2 matrix, but you're not expected to remember that. Okay, which one's minus and which one's plus is all straight out of the notes that you get in your exam. Okay, so I'm going to show you this. This is compared to variation of parameters, like the most totally basic thing you'd ever seen compared to variation of parameters. But if you're going to get things right, you might as well get the easy things right. So odd and even extensions. And when people were doing this in the Maths Learning Centre, they were sort of getting it wrong. And the ORMS people in, do you remember which exam that was, Sana? I think it was 2012. They got one of the answers wrong. Yep. 2012 question 3. The drawings of the odd and even periodic extensions in the ORMS solutions are wrong. So, okay. So the way this works is, with odd and even extensions, is that you begin with a function that only exists sort of over here. And, you know, who knows what it will look like, but let's just pick one. You know, just as an example. And then what you have to do is you have to extend it to be a periodic function in either, and you get to choose whether it's going to be odd or even. And the odd one, when you do its Fourier series, they'll all be sines, and the even one, when you do its Fourier series, they'll all be causes. So, if you want to make an odd or an even periodic extension, you have to make it odd or even first, and then make it periodic. Okay, so don't make it periodic and then make it odd or even, because the final result then won't be periodic overall. So first odd or even, and then periodic. So, even extension. And note that this is also called the half-range extension. Don't know why, but that's what it's called. So first you make it even. Even functions have symmetry this way, around the y-axis. So if you flip it that way, then you'll make the even extension first, and then we'll make it periodic. So first you flip. Okay? Okay, so you copy it this way. And then what you'll have is this whole bit here, and you copy that both directions on your x-axis. So then copy. So I have this bit here, which was this, and I copy it. I copy it here, and here, and here, and here, and forever. So I'll copy all of that. This is a very bad drawing, but this is the idea behind it. Okay? You'll flip it, and then you'll copy it, and then it will be periodic and even. My recommendation is to do all this on your scribble paper and only draw one fancy diagram on the exam. Okay? To do an odd extension, odd functions have symmetry rotationally. So I'll take that and I'll rotate it around the origin. You have also got a different choice. You can flip it this way and then flip it that way, and it will produce the right answer. And that's a little easier than rotating. So I would actually do a flip, flip, and that will get me the right answer. Double flip. So what I'll do is I'll keep this side the way it was. Okay, I've already flipped it once to get the even one. If I flip that upside down this way, it will produce the odd one. Like that. So I've taken that one and I've gone like that. And then I take what I get and I copy it. So I've got my original graph. And I copy it both ways. And so on. It has the tendency to ask you to draw 3 periods in the exam. So, okay, flip it, or flip it twice if you want to do an odd one, and then copy it. That's drawing odd and even extensions. And that's. Does he ever ask you for the formula for them? No. Okay. So that's how to draw them. I just need to give you something that's simple that you can do, because there's no excuse for doing something, for not knowing how to do something that is really just a drawing. Okay, no matter how difficult all the rest of it is. And you know, the people marking your exam, especially your lecturer, will go, "This is so easy, why aren't they getting it right?" And it'll be in such a bad mood. And if you want them to be in a good mood, you want to do the simplest things right. So that's my instructions for that. So any requests now? Yep.
When doing undetermined coefficients,
Yep.
when you put a non-homogeneous, so you got an Rx term, I found that for exponentials, so e to the x, it's then x, e to the x. So you get, and then, but for e to the minus x, they put x squared there. I don't understand why.
Okay. Have you got which question what that was? Because I have a feeling I know what it is.
First question of 2012, I think.
2012 seems to be that much harder than the other ones.
Yeah.
Note that this is the first exam that Trent wrote. But at least you know what to expect, right? I'm not trying to freak you out. Knowledge is power, okay? Don't be afraid of the known. Okay. So No.
The last part where it says what would be the Rx for these.
Oh, okay. No, that wasn't the 2012. That was a different one. Look, so this is undetermined coefficients. So undetermined coefficients was a method for finding a particular solution for linear constant coefficient differential equations. And it will work for any order, so you'll be able to have like third order, fifth order, and it'll always work. So method for finding YP for linear constant coefficients. Okay. So what you do is, as you rightly said, you look at your Rx and you probably should put it in standard form first and then look at your Rx. So look at your Rx and then choose something that looks like that but with undetermined coefficients. So, but there is this problem that happens if your original solutions already had the thing you would have done. That's when you multiply by x. So that's probably what's going on there. So, as an example, so the one that we had before, just as a guess, suppose we had this one. So we'll just skip all the bit where we find the homogeneous solutions, but homogeneous solutions, via the characteristic equation and all of that stuff. They came out to this before. They came out to that. So if you were going to now try a particular solution, normally you try the e to the x and you just try constant times the e to the x. That's normally what you try. But e to the x is already one of the homogeneous solutions, so we can't use that one because it's already one of the homogeneous solutions. And the next what you do is you try multiplying by x and see what you get. And that might work. But that's already one of the homogeneous solutions, so we can't use that. So what we'll have to do is this. Use x squared. Okay? So because both of these were already part of the homogeneous solution, we couldn't use them. So we had to use that one. So can't use it. It's part of the homogeneous. And so you just keep adding a power of x until you get to one that you haven't already got. That's probably why.
Yeah. The original question was in 2011. I remember now.
Okay.
Yeah.
But that's probably what was happening. Okay, and that generally works, and you're not allowed to use anything that appeared in the original.
Is it only for exponentials, or is that for?
That's for everything, anything. So if the original had like cos 2x, you couldn't use. If the cos 2x happened here, you couldn't use it, and you'd have x cos 2x. So you'd multiply by x. I think that's what he said in his notes. Okay. I find that. Yeah, that's basically it. If you have one that's a combination, so in 2000 where they're multiplied together, something like this, e.g. Rx equals x sine x. The rules, I've gone blue. The rules say that if you have just sine x, then what you should use is an a sine x and a b cos x. And if you have just x, you should use like an ax plus b. And so you want to do a combination of that. So you want to have the constants and the x's. So I would try the And that's really thinking ahead. Normally what you'd expect is you'd write like a plus bx in brackets and like c sine x plus d cos x in brackets. But people have been pinged in the past for not expanding that out and choosing individual coefficients for them. So you can sort of say, what if it was just 1 plus x and sine x cos x, expand that all out, and then just put coefficients next to everything. So, yeah. But you're supposed to have every possible combination of what you would have done with this with every possible combination of what you would have done with that, and they all have coefficients. Yeah. But it seems tradition to just ask you what the form is and not ask you to find the coefficients. And if they did that, that means there'd be something else somewhere else that would be a little bit easier, because that takes time. Any more? We're only 20 past.
So how do you pick the in the form of?
How do you pick in the form of?
Yeah.
Like for this undetermined coefficients?
So 1 minus cosine 2t would just be a plus b cosine 2t? Sound right?
Like that?
Yeah.
Okay, so each piece of it has its own rules. If you see a constant, then you try a constant. So that would just be a. If I see cos 2t, I have to put in both a cos and a sine. Because when I do its derivatives and put them into the original formula, there'll be both coses and sines.
And same way if it's just a sine?
Yep, and same way if it's just a sine. If they're both already there, then you don't need to put 4 of them in, you only need 2 of them. So if there's a cos and or a sine, you put both a cos and a sine. So I think the table in the lecture notes was if you see just a constant, then you'll try a constant. If you see an x, you'll try ax plus b. If you see x squared, you'll try ax squared plus bx plus c. That's that idea. If you see cos, and a number times x, or x or t or whatever, and or sine 3x, doesn't matter whether, if they're both there, if they've got the same number, then you'll do a cos 3x plus b sine 3x. Okay, so you don't need them both, but if they are both there, you don't need to do 4 of them, you just need 2 of them. And if you see an e to the 2x, then you'll try a e to the 2x. Except if it's already as part of the homogeneous solution, then you'll keep multiplying by x until you get one that isn't. So, yeah. And if you've got an e to the 2x and an e to the 3x, then you'll need them both in the solution. If you've got a cos 3x and a sine 4x, then you'll need an a cos 3x, b cos sine 3x, and a c cos 4x and a d sine 4x. So you need one for every combination that's there.
And I see there's no examples there of like a quotient.
No, that's too hard. Though interestingly, the one that we had before that did have a quotient, it was a 1 over x, came out to be 1 over x. So it's probably true that it comes out to a quotient, but as far as I know, that's just too hard. And the quotients are the sort of thing that you would use variation of parameters to do. This is all going on purely what's in your lecture notes. So, anything else? Can talk all day. Yep.
How does oscillation and damping questions affect what type of multiplication?
This is interesting because I'm not sure. Mainly because there haven't been any oscillation or dampening questions in the exams for the last 4 years. We may take from that what we will. I mean, but there was 16 lecture slides on it. I think the thing is that your damping and oscillation things are all second order with constant coefficients. And that's why they were at the point that they were in the lecture notes. So if you actually look closely at the equations that are there, you get they're all second order with constant coefficients, and there might be a an Rx or there might not, and sometimes it's a sine or a cos, and sometimes it's something else. So looking through the notes here, which I made very small so that I didn't waste my ink, it's got undamped, free undamped and free damped. They're homogeneous, and I use my ordinary methods of doing a characteristic equation and figuring it out. Sometimes if they come out with complex roots, you'll get sine or a cos. If they come out with real roots, you'll get either the x's. And then the next ones come out being damped, but you're just dividing by something, and it's still just a number. So they're all just the constant coefficient ones. So presumably you could probably ignore the fact that it's a free oscillation or a damped oscillation and just pretend that it's just a differential equation. Because I have a feeling that what he'll do, which is what he always seems to do in the past, is that he'll say, consider the free damped oscillation, and he'll just give you the formula. And from that point you just go, well, let's just pretend it's not anything important and just look at the formula and you'll do it from there. I think that's my instinct, but I couldn't know for sure. Whoever asked that, was it you? Yeah. Yeah. Whispering over there. Yep.
Just in the lectures, when finding a Fourier series for, like, you did an example of an even and odd function.
Yep.
So you draw it all up and so what the formula he uses, like, you find an and bn. He uses a different formula than the one that's on the formula sheet for the exam.
Okay.
I don't know why.
I'll have to look it up, hey?
He does an example in lecture 16. It's example like 16.5.
Three, 5. Find the Fourier series of mod x.
Yep.
Yep.
So he goes through, he proves that it's even. So when he finds A naught, he uses a formula which is 1 on L outside of the integral of 0 to L of f of x dx.
Mm-hmm.
And in the formula sheet, it's a different A naught.
Ah, okay.
And A naught, AN, and BN are all different. So once he uses in the lecture.
Yep, let me get my formula sheet out. So in the formula sheet, there's a version with pi in it, but we can deal with that. And there's a version with L. So you've got, and this is from the formula sheet, you've got that f of x is A0 You got this?
Yep.
Okay. And then he says that A0 is 1 on 2L, the integral from minus L to L of f of x dx. Yep.
Yep.
And AN is just 1 on L from minus L to L of f of x cos n pi x on L. And BN is 1 on L from minus L to L of f of x sine n pi x on L dx. That's the formula sheet version. These are called the Euler formulas, or Euler, but apparently he was, European and supposed to be Euler. So, cool. The thing is that if you use an even function or an odd function, think about what happens if f is even. Then it might be, something like this. and the integral from 0 to L is going to be the same as the integral from minus L to 0. So this goes from minus L to L. So this is going to be the same answer as twice the integral from 0 to L. And the two will cancel out. That's why. So, and it'll happen with all of these because an even function times an even function is still even. And even if it was an odd function, the A0 would come out as 0, because odd functions from minus anything to the plus the same thing is always 0. And odd functions, an odd function times an odd function is actually an even function, so the same thing happens. So if you get an even function, the integral from minus L to L of something is the same as twice the integral from 0 to L. And so you can change your formula. And if it's an odd function, so this is something involving cos, right? Then from minus L to L of f sine will be even, and so it'll come out to this. So that's why. It just makes you work a little shorter because you've got all these lovely zeros. And it means that you're technically using your original function, which only worked from 0 to L anyway. So yeah, so technically there is this sort of, there's the version with pi, there's the version with L, and then there's a version for even and odd functions. Yeah. But you can still write this version down and sort of remember that this is how it works out. Yeah. And don't forget that for 0 it's 2L, and for all the other ones it's L. I forgot that helping someone with one of the assignments. Well, actually, I didn't know that when helping someone for one of the assignments. And it's because this is actually orthonormal basis from Maths 1B algebra. Yeah. And this is the length. Like, this is the dot product. Like, it's awesome. But, you know, awesome doesn't help you do it. So, yeah. But that's cool. Yes?
Just on ordinary or singular points.
Yep.
Could you just go through those?
Okay.
Just popped up on the sign a few times.
All right. So, now let me see. I do have my list of terminology here. A singular point is a point where, okay. So you've got something like this. So second order. Because we didn't need any of this crap for first order ones, we could just do most of them with integrating factors and stuff. A singular point was a point at which, if you sub that into P and Q, at least one of them or one of their derivatives is undefined. So you've got that. And he normally calls it x0. You'll get that Px and or Qx are not analytic, they say, at x equals x0, which basically usually means that they're undefined when at that point. You don't technically need the actual function to be undefined there, you just need one of its derivatives, but usually it's the function itself. So, and there was an example in the lectures where there was like a root x. That's technically not analytic at that point because it doesn't exist on the at 0, because it doesn't exist on the other side of 0. It has to sort of be continuous there as well. So. Okay, that's a singular point. A regular singular point, which I was just talking to someone about this morning, is one. Or ordinary, did he call an ordinary singular point regular? Regular.
Singular points may be regular or irregular.
Yeah.
Singular points occur when you And that's about it.
Yeah. A regular singular point. Then what you get is that if you take this as a formula, just ignoring the fact that it's not defined when x is equal to x0, and you multiply its formula by this, okay? And you take this as a formula and you multiply its formula by this, and you get a brand new formula. If those formulas are defined when x is equal to x0, then it's a regular point. Regular singular point. So this was my example. So suppose we had something like x squared minus 1, y double dash plus x, y dashed plus x minus 2y equals 0. First you have to write it in standard form. Like that. And then so a singular point would be, say, x equals 1, because these aren't defined when x is equal to 1. So you don't need both of them to be undefined, just one of them. So since x over x squared minus 1 or x minus 2 over x squared minus 1 are undefined at x equals 1, we get a singular point there.
And negative 1?
And negative 1. We have singular points at x equals 1 and x equals minus 1. Okay. And a regular singular point, and in fact if they're all polynomials it's always going to be a regular singular point usually, but a regular singular point would be if I multiplied that px and qx, that's my p and my q, by the relevant x minus whatever, then it would come out to be analytic at that spot. So, so to decide if regular, you'll get, so px times x minus 1 would be x over x squared take 1 times x minus 1, which is x over x plus 1, x take 1, factorise in the bottom, and they neatly cancel out. And this is analytic when x is equal to 1, because it's not 0 on the bottom anymore. So, and qx times x minus 1 squared would be x minus 2 over x squared minus 1 times x minus 1 squared. That's going to be even better. Crap. So I'm going to get x minus 2 x minus 1 over x plus 1, and that is analytic as well. And so this is a regular singular point at x equals 1. So, analytic at x equals 1. So therefore x equals 1 is a regular singular point. I won't do the other one, it's probably regular as well. The times when it might be not regular is if there's already there was already an x minus 1 on the bottom of this. And so you haven't, if there's already like x minus 1 squareds or something on the bottom of one of them, if there's already too many of them down there, then when you multiply by the x minus 1 squared, they won't all cancel out and it'll still be undefined at that spot. So, and there was a theorem that went with regular singular points, wasn't there? Just excuse me for a moment, because my wife dared me to do this. Yes, sir, Rooney, posituni, we are going to the textbook box, where David's really good at looking up theorems, and every theorem rocks. Theorems rock! Thank you. If you've never seen
Idol,
Pink...
David.
Sorry?
Australian Idol.
Thank you. No. Couldn't think of anything worse. Well, actually, MasterChef, that'd be worse. Don't know why they have MasterChef. It just teaches people that cooking is stressful. We want regular singular points, don't we? 212. Any differential equation of the form where there's x's on the bottom, so a point where x0 is a regular singular point, has a solution that looks like a power series. So basically it's saying the theorem was if 0 is a regular singular point, then at least one of the solutions will be y equals x to the r n equals 0 to infinity a n x to the n for some r. So basically it's saying you're allowed to use this power series thing when x is a regular singular point. Do you want me to go through the power series thing?
Yes, please.
So that's called the Frobenius method, apparently. And last year we didn't get any power series in the...
2011 they did this one.
Yeah. Yeah. So you'll notice that the lecturer, who wasn't Trent in this year, but it's probably roughly the same anyway, the lecturer will tell you that you should use a power series. And what it says, if you've seen it in 2011, question 3, it says, consider the second order ordinary differential equation x y double dashed minus 2 x minus 1 y dashed plus x minus 2 y equals 0. And he says, since x equals 0 is a regular singular point, which it is, because if I divide this through to be in standard form, then both of these will be analytic if I multiply them by x and x squared. Okay, then that means that there is a solution of the form power series. So okay. So that's one of the solutions. And I know that because basically if I do my standard form, I've got at most a single x on the bottom of this and at most an x squared on the bottom of this. It doesn't have to be an x squared, it's just anything less than x squared will be fine. So basically that's how it works. And then he says, write down expressions for y dashed and y double dashed. So that's what you would normally do. Because what we're going to do is we're going to sub this in, that's an A by the way, we're going to sub this into there and see what we get. So y dashed, we're just going to differentiate each term separately. Like that. And then y double dashed, bring the power down, make the power less by 1. And there are our solutions. Now this is one of the situations where writing it in standard form helps you to tell whether you're allowed to do this, but for actually solving the equation, writing it in standard form is a bad idea. Okay? The reason why this is going to work is because it's polynomials times the x times the y's and the y dashes. So, and that's why the power series thing is going to be helpful, because when I multiply the y double dash by x, I'll just put the power up by 1. Okay. So he says, substituting equation 3 and its derivatives into equation 2, that was equation 2, this is equation 3, and rearranging some terms and shifting some indices yields the intermediate result. I'm going to do all of that. If Trent does something like that, don't do the intermediate steps because he's trying to make it shorter for you. But you need to see how the shifting of the indices works, because lots of people are confused by that, and that's partly because it goes all the way back to something that was in Maths 1A in about week 3. So it's at least a year ago, if not more. So sub into the differential equation. So this is in general a good method for polynomials times the y double dash and the y dash and the y. I presume that you could even use it if it was like x minus 3 here. You just have, instead of x, you have x minus 3 to the m plus r instead. But I don't think they ever ask you to do that. So we sub it into the differential equation. So I'm going to first need to figure out what x times this and minus 2x minus 1 times this and x minus 2 times this is. So let's see. X times y double dashed that's not an x, that's an m. So I'm timesing them all by x, so my powers of x will all be 1 higher, so that'll be a minus 1 now, because before it was minus 2, and I've times it by x, so now they're all 1 bigger than they were before. Okay. So my minus 2, x minus 1, y dashed, just expand that out. I've got minus 2x y dashed plus 2y dashed. So I'm getting, so my y dashed was this. And I'm doing first minus 2x times that, so I've got a minus 2 here, and the x is going to go up by 1. And then the other one is 2y dashed, so I'll get my y dashed. Minus 1, and I'll multiply it by 2. Okay? And then my x minus 2y would be x times y minus 2y. So I've got y is m equals 0 to infinity am x to the m plus r, and I times by x, so it goes up to plus 1. And my y is am x to the m plus r, and I'm timesing it by minus 2. And then when I sub that all into the differential equation, it'll all come out as 0. What's the aim here?
They want the result to find the indicial equation.
So I need an indicial equation. How do I get that?
You pull out the r minus 1.
So pull out coefficients of r's and things.
Yeah, coefficients of m and coefficients of r, whatever else you have.
Okay. I'm just going to look that up because I want to remind myself how that worked. Equate the x to the r coefficient to 0 to get the initial equation. Okay, so what I need to do is I need to, no matter what I'm doing with these power series things, I think what I need to do is lump this all together into one big thing that has like crap times x to the m plus r. And then all with a big sum, and all of that's equal to 0, so all the individual coefficients must be equal to 0, and you set m equals 0, and that gives you the r coefficient. Is that right? Yeah? I think that's right. So, all right. So what I need to do is change them so that all of their powers match properly. So that's this shifting indices thing. So you notice that this one's got an m plus r. And this one's got an m plus r. These two are m plus r minus 1. And this one's m plus r plus 1. So I need to just compare what I'm supposed to get. So he leaves one of them with an m plus r minus 1. Why does he do that? Aren't you supposed to convert them all to m plus r? Yeah?
You need to convert that one to m plus r, but then you've still got one summation starting at 0, so you need to plug in
Yeah.
1.
Rightio. So, because that one's got an m minus 1. So what he's done is at least one of these he's converted to yeah. So back in Maths 1A, when you saw something that had like a plus 1 up here, you could subtract 1 here and add 1 to here. And that's shifting the indices. So, and the same deal works for all of them. And then there's this other trick that goes, well, suppose I wanted to do the same trick here. I could add 1 here and subtract 1 to each of these. But that's not as nice as I would like because I'd be starting at m equals minus 1, which doesn't make any sense. So normally what you do is you say, well, the first one is 0, but this one's got an r in it. So that's why he's left one of them as an r minus, these two as an r minus 1, I'd say. Why have I not got the same? This here is his first one. But why is that not combined with that one? This bothers me. Okay. But he's shifted some indices. Oh, I hate this. I have read the original equation right, haven't I? Minus 2x minus 1. Yep. Okay. Rightio. Well, at least we know what the answer is supposed to be. So, this one can be shifted to start at 1. So I can subtract 1 from the m's here. M minus 1, actually m plus r, and add 1 to the m's here. Okay, subtract 1 from all the m's in this bit, add 1 to these, but infinity plus 1 is still infinity. And leave this one as it is. And this one, I have a feeling similar to that. Someone's whispering because they've figured something out that I haven't figured out. No?
We were just thinking, if you convert it into standard form, would it make life much easier than start?
No. Would it?
It would.
Yeah.
Because you'd be dividing by x's instead?
Yeah. That's all the plus 1 into the plus term.
Yeah, probably.
And the whole term switches like.
So you just divide absolutely everything by x, and everything comes down 1.
Yeah.
But wouldn't everything come down 1? And that would make this starting at like minus 2?
Yeah. And then you can make m equals n plus 2, k plus 2.
Okay. Radio. Bothers me though. Bothers me. See, it all seems so simple when I did it in the assignment. Okay, so you're saying I should divide everything by x?
Yeah.
Okay. I'm fairly sure you're not supposed to, that's supposed to make it harder, but maybe it doesn't.
Because I remember doing that for the assignment as well. Just so that you don't have to index shift twice.
Oh, I see. So basically, if I'd started with the standard form, then what I would have had is everything would be one lower. Yeah?
Yeah.
This is the sort of thing we want to figure out now, not during the exam.
The thing is, in 2011 exam, they've already done all this.
Yeah, I just want to know how to do it, that's all.
Yeah.
Yeah, all right. I'm going to persevere just for one more minute. Yeah, okay. But everything's... Oh, I get it. Right? Everything's one power down. And so this and that's not how we got what he's got there though.
What question is this, sorry?
2011, question 3. Okay. Yeah, okay. So your shifting indices always seems so nice. If there's no R there, then you can just say, well, if M is 0, then the whole thing is 0 anyway.
Don't you call M plus R minus 1K and then rearrange?
Do you?
Sure.
Okay. Not having been to the lectures, I don't have all his fancy, or all the examples. But you're saying that to figure out the initial equation,
So you call M plus R minus 1 K plus R and then rearrange.
oh, that's just shifting the indices. Yeah.
Isn't that what we want?
Oh, yeah, that's what we were doing. I just wanted to see what was going on. So this one's coming out like this. So I'm just going to start where he was because I think there's going to be one more index shift. You'll need to shift indices in the first summation. So when we shift indices in the first summation, we want the R to be 1 bigger so that it's M plus R. That's going to start at M equals minus 1. Is that right? Because then it'll all be X plus R. Yeah? So that's saying that I should really start at minus 1. Am I allowed to do that? Don't see why not. So what I did is I added 1 to all the M's here and subtracted 1 there.
Yeah.
Which is what I should have done in the other one. I was just worried about starting at M equals minus 1, but it apparently doesn't matter. So, what you do now and I'm just a bit distressed that this is going to come out to some sort of is you apparently set so this thing here, it's equal to 0, so every single coefficient in the entire thing is equal to 0. So if we find the coefficient of x to the r, which happens when m is 0, we're going to get A1, tell me if I'm wrong, r plus 1, r plus 2, minus 2A0, r plus 1, plus A minus 1. Is that wrong? Or does the additional equation just involve some other stuff?
No, I think all your m's starting at the same point, so you're going to have to do, you've got minus 1 and 0, minus 1, you're going to have to plug in minus 1 and 0.
And those terms end up being 0.
Yeah.
So you want them all to be AM and you don't care about the others?
No, they can be, you might have a term that's going to be a to the m, am plus 1, but the m's underneath the summations, they need to all start at the same point.
He's saying, right, the first series out, the first two terms out explicitly, and then the second series write one term out explicitly, and they all start at m.
So they all start at 1?
Yeah, and go from there.
Okay. It looks like the strategy is they're all supposed to have an AM and not an AM plus 1.
So
Is that the idea?
One of them will have an am plus 1 because you'll have your term times am plus 1.
All right, well, my book says I think that they're all supposed to be the same. But you're saying that we should go, that this one has an AM,
That's good.
this one has an AM, this one has an AM minus 1. So doesn't that mean that we should make this one have an AM and not shift the first series of this?
I think for that, we're trying to make all the summations start from m equals 0.
Okay.
So we need to have that as one big summation. So we need to write the first, when m equals minus 1, the first two terms explicitly. So when it's m equals minus 1, m equals 0. So we can have it as m equals 0. So we can have the whole thing as one big summation as m equals 0. Where m equals 1, sorry.
Yeah.
So you're saying
That's right.
So run out the first two terms of the first series.
So you're saying start at 1,
Yeah.
2?
Yeah, and then you'll have the first two terms out the front of that.
Oh, I see. So
So start at m equals minus 1 and then
Yeah, and for the
0.
second series, you write one term out and have one term out the front. Then you can add them all together.
so that they all start at the same spot.
Yeah.
Yeah.
Right.
Nice, those terms end up being 0.
Okay. Did I shift it first? So it said x to the m plus r?
You could go from, like, is that thing you've just scribbled out on the page above, is that what he had in the exam? Or
I'm not sure. This is the point where I don't know what's going on. And part of the message here is there comes a point when David just hasn't done it. And it means we have to talk to Trent about what's going on there. So, see in my book here, it says they've got things that start at different spots and they've arranged them all to be AM somehow.
maybe they're going to the same thing, but
Going for the same thing.
maybe, no, like, book strategy versus trend strategy is obviously
Different. AM, m plus r plus 1, x to the m plus r minus 1. So he's saying we have to shift the first one so that it shift indices in the first one, and you're going, well, the first, when m equals 0, the first one is x to the r minus 1.
Yeah.
I think you write all that to the power of x to the n plus r and change the indices and then write out the terms.
Okay.
So just write the terms x plus r.
Write them all as m plus r first.
Yeah, x n.
Crappity crap. So subtract 1 from these so that this is all m plus r.
Yeah.
Like that.
And then write the value, like suddenly m equals minus 1 outside so it changes to a constant without the without the summation.
Okay. So you're saying now write out the first couple.
Yeah, so then, like, because see how the last series starts at m equals 1, and then the
Yeah.
other two start at 0 and negative 1. So you basically just,
Evaluate the first summation at m equals minus 1.
and at m equals 0.
So we have a equals a0
Yeah,
r,
yeah,
r plus 1, x to the r minus 1.
yeah,
Yep.
yeah, then to 0, m equals 0.
a1, r plus 1, r plus 2, x to the r.
Yep.
Yeah,
And then do summation from 1. Write out.
And then you've got plus starting at m equals 1.
yeah.
And you do that for 2.
And
Yeah,
this
then
one
you do it for the second one as well. Just
minus
with
2, a0, r plus 1, x to the r,
Yeah,
plus m equals 1 to infinity of crap.
yeah,
And this one's already m equals 1 to infinity. Yeah?
Yep.
and then all that crap out the front of the summations will probably turn 0. Is what that's. Will probably just turn out to 0.
Okay.
Yeah, so your final solution will be a something m plus 1 equals something times a m minus 1. It'll be like a quotient with powers.
Right. I think that we're supposed to be able to divide by the a to get an equation that just involves r. Where's that coming from? Because I reckon it comes from here. I think it's r times r plus 1 equals 0.
Yeah, if you take out all the coefficients of x to the r minus 1, get that equals 0, and then you solve for r.
And that's your initial equation. So what we should have been doing is saying, what's the smallest power of r that appears when I sub stuff in here? And it's r to the minus, and it's r minus, what's the smallest power of x that appears when I sub in values of m, and it comes out as r minus 1?
Thanks, because you're going to have r minus 1 and r.
Yeah, because these are all x to the r, they're different. And this is giving me, r plus 1, and this one, these all start at 1, so these all start at x to the m plus r plus 1.
Yeah.
Though this one, yeah, these all start at x to the r plus 1. Yep? Yes. So what I want to do is I want the smallest possible m that appears anywhere, and that's m equals minus 1. Okay, I think we've got it now. We're basically going, look, we're going to shift them all so they're all m plus r, right?
Yeah.
And since they're all m plus r, I pick the smallest m that appears absolutely anywhere, and it's this m here. The smallest m is m equals minus 1. And so we're going to choose x to the r minus 1 and find that one. And when m is equal to minus 1, I've got a minus 1 plus 1, minus 1 plus 1 plus r, minus 1 plus r plus 2, x to the minus 1 plus r, which is a 0, r plus 1, x to the r minus 1. And that's equal to, on the other side of the equation, it's equal to 0. Equals 0 x to the r minus 1. So therefore r plus 1 is 0, and that's my initial equation. So most of the rest of that crap was actually unnecessary. Yay! So, right, so I think that what we're doing here, just to make sure that we've got this right, you shift them so they're all m plus r, and then you find the smallest possible power of x, and you find its coefficient. And then you go, well, smallest possible power of x happens when m is equal to minus 1, and in our case there was only one of them. But if it happened when m was 0, I might get one bit from here, and one bit from here, and one bit from here, and I'll have to lump them all together. Okay, I think we've got it. So then we're getting r equals 0 or minus 1. Yep. And they're saying for r equals 0, find an expression for a1 in terms of a0. And for that, we could use the term for x to the r, where n is 0. So I think that you use the next term to do the next thing. Well, we did have an equation here. We had back here when we used x to the r, we had this bit and this bit, which were the x to the r term. So if we have that, so the second smallest m is m equals 0. And if m equals 0, then we can get that from the first two. Here, we've got a1, 1 plus r plus 2, x to the r, plus, minus 2, a0, r plus 1, x to the r. But this one doesn't have an m equals 0, so I won't do that one at all. Because it doesn't have an x to the, I can't put in m equals 0. And so I've got this equation. I've got a1, 1 plus r plus 2, minus 2, a0, r plus 1 equals 0. But r is 0, so I can sub that in and it will tell me an equation that relates a1 and a0.
Yeah, and that's how you get your
But r equals 0, and so I've got a1 times 1 times 2 minus 2a0 times 1 equals 0. So 2a1 equals 2a0, and a1 is in fact equal to a0.
Why don't you sub in -1 for r?
For r?
Yeah.
Because they told me to use 0.
Right.
But you would also do -1 separately and see what you had with that. And so now I know the first two. The next term, I can just use m equals m and see what I get. So when m equals m, maybe m equals n, but I don't know, it doesn't really matter. I can go back to my equation and go, well, I've got a m plus 1, m plus, r is 0, right? But I'll just put it in. That's the coefficient of x to the m plus r, minus 2m, m plus r plus 1, plus a m minus 1. And they're all the coefficients of x to the r. And r is 0. So I've got am plus 1, m plus 1, m plus 2 minus 2am m plus 1 plus am minus 1 equals 0. And I can get this recurrence relation that has am plus 1 equals stuff in terms of am and am minus 1. So am plus 1 and that's a perfectly good recurrence relation. So now I've got that A0 is A0, yep, and A1 is, because we don't, do we have an initial condition? No. So A0 is A0, A1 is also A0, because we got that. And A2, according to this formula, which is when m is 1, will be 2A1 times 2 minus A0. So that's when m is 1.
That'll just make them all zero, all the same.
Sorry?
That'll make them all the same.
Will it? That'll be fun. Fairly sure that will probably happen. 2, 3. No, I've got A1, 0, 1, 2 now, because A1 is A0, so I've got 4A0 minus A0 over 6, which is actually 3A0 over 6, which is A0 over 2. That's what I've got. So the first three terms of my power series. So my power series is x to the r, is am x to the m plus r. So y is actually going to be a0 x to the 0 plus, and r is 0, so that's just a0, plus a1 x to the 1 plus a2 x squared, so that's a0 plus a0x plus a0 on 2x squared. And that's the first three terms of the series itself. I think that's it. So technically I suppose I could choose a0 to be whatever I want. This is a general solution, so do we leave it with an a0? Yeah. Okay. Right, so actually much easier than it seems. So way back here, even if he hadn't given me that, I don't even really need to technically shift the indices at all. I do, so that I can know the m plus r thing. Yeah, so I need them all to be x to the m plus r, and that's the aim, so that I can have the coefficients of those things. Rather than the AMs matching, I want the others. X to the m plus r, find the smallest one, find the second smallest one, and then I can figure out a recurrence rate relation for all the others. Cool, and that's why we make lists for ourselves, right? So we need x to the m plus r in all of them. Smallest m gives you the initial equation. Value of r and the second smallest m gives you or the third, or however many there are, gives you the relationship between A0 and A1, or whatever they are, and then the A0 and A1, and then the coefficient of x to the m plus r gives you a recurrence relation.
Can you explain the relationship between A0 and A1? I've got in my notes here from one of the major assignments that A1 was just multiples of A0.
That's what happened to ours.
Can you just explain it? I kind of got a bit lost there.
So back here, nope.
In mine here, I've got, so if I say A0, A1, A2, the A1, A3, A5 cancels out. Does the odd.
Oh, okay. I'm not sure about that. I don't have those notes. But I've got back here when I got my second smallest m, I ended up with this single equation here that involved A0 and A1. And it'll be different for everything, but it turned out that I had A1 equals A0, but if this had been a 2 and this had been a 3, I would have got A1 equals 3 halves of A0. And depending on what the equation is.
Write out everything in terms of A0.
Yeah. And if one of them came out as 0, it might mean that every second one of them is 0.
Yeah.
That's where your recurrent relationship is just awesome, because you might figure out that A0 is 0, and then every even one might depend on A0. So then you just don't even worry about even subgroups, you just go all the odds or whatever.
Yeah. So I can't predict that because I don't know enough about how this all works. Yeah. So I don't think you had to write it as a in standard form to begin with, because I reckon we could have got it from anywhere. Just find the smallest m.
Yeah.
And sub it in. Yeah. But you would have to probably do more shifting overall, but you know, shifting is not something that gives me pain, but gives lots of other people pain, so somehow between here and here, dot, 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 we managed to get to here. Yeah. All right. Well, don't know if I just confuse people more, but at least they'll know that they can't come to David for this anymore because he doesn't know it.